In this video, we're going to find the electric field of a conducting sphere of radius a with uniform volumetric charge density. Pay attention to the wording of the question, especially this part, uniform volumetric charge density. Let's start by drawing a diagram. So this is the sphere, that is the radius a as quoted by the question, and E will go out radially in all directions. This is because we have a uniform volumetric charge density. Charge is spread evenly all throughout this solid conducting sphere. So that gives us a clue as to what rho is. Rho will have units of coulombs per meter cubed, because it is a volumetric charge density, and because this volumetric charge density is uniform, rho will simply be the total charge enclosed by the sphere divided by the volume of the sphere. I'll write this out more clearly in the next slide. So here you can see rho has units of coulombs per meter cubed, and it is equal to the total charge in this sphere divided by the volume of the sphere. And of course the volume is 4 pi r cubed over 3, but because r is a, the radius is a, I've substituted that in over here. Now the next step is to pick a Gaussian surface. You'd be correct in thinking that the sphere would be the easiest to use, but there's a catch. Because the sphere has a uniform volumetric charge density, we need two Gaussian surfaces. One with r greater than or equal to a, r being the radius of the Gaussian surface, and one with r less than a, on the inside of the sphere of uniform volumetric charge density. You'll see why when we solve the question. Here's a quick review on spherical coordinates. I'll just flash the slides by because I've already talked about the techniques of using them in the point charge example. Just as a quick review though, what we're doing is we're just cutting up this sphere into tiny and tinier bits until we get this prismic shape that makes it very easy to see what a ds or a dv element is. If you're confused by these terms and this doesn't seem to make sense to you, please watch the first example on Gauss's law and review your 200 level math course notes. Here you can see how we pulled out this shape from the previous slide, and if we cut it further we get this prismic shape over here, and the dv element is found just by multiplying these dimensions. So you multiply dr, r d theta, and r sin theta d phi, and there's no unit vector associated with the dv element. Let's find the Q enclosed for each Gaussian surface. We'll start with r greater than or equal to a. We know this dv element from the previous slide, and we know we can find the Q enclosed just by taking the integral, the volume integral that is, of rho dv. Note that rho is just Q total over 4 pi a cubed over 3. So just plug in the values here. dv goes over here, and rho would go in over here. And we can find that Q enclosed is just the Q total of this sphere of volumetric charge density. As an exercise, prove to yourself why this is conceptually. Try thinking about the units of rho and v, and try and visualize what this may look like. Now let's find E. This is again for r greater than or equal to a, and this is what we have for Gauss's law. And now we can just plug in the values. We know what Q enclosed is. That's just the Q total for the sphere of volumetric charge density. And we're looking for E. And we know it'll go out radially in all directions. And we know the ds element from our previous videos on Gauss's law. After plugging in all these values and taking this integral, we see that E is just Q total over 4 pi epsilon naught r squared, all in the a hat r direction. Does this remind you of anything? Quite similar to the point charge, isn't it? Now let's find the parts for r less than a. Here I'm solving the Q enclosed for r less than a. I'm using prime notations in the dv element. Notice it's essentially the same except just you put primes here on the r's. The reason I've done that is because now for the radial component I'm not going from 0 to a, but I'm going from 0 to r being the radius of the Gaussian surface, because that is the limit of what encloses the charge. By doing that and solving this integral, I have Q total over 4 pi a cubed over 3 multiplied by 4 pi r cubed over 3. And here you can see that we have a different Q enclosed on the inside of the sphere. And if we have a different Q enclosed, we will certainly have a different E by Gauss's law. Let's see how to find this E. Well, here we know that E must go out radially in all directions, and the ds element is still the same. Now if we solve this integral on the right hand side, it would be the same as what we had before, but the left hand side is different. Therefore we have a different E given by this equation. After we've solved the integral, it's just basic algebra. That's how I found E. And that's just a summary of the final answers. Thank you very much. I'll see you in the next video.